Ilya graduated as a MSc in space physics from Leningrad Polytechnics in 1988. Then he worked as a researcher at the LOF Physical Technical Institute in St. Petersburg in Russia, where he got a PhD in astrophysics in 1995. After that, he was a postdoc at INFN, which I don't know what it stands for. Okay, yeah, in Milano, Italy. Sounds Italian. And CERN and NASA from 1997 to 1999. He has been the head of the Cosmic Rays Station of the University of Oulu in Finland since the year 2000. And in 2012, he became full professor at the University of Oulu. And since 2014, he is the vice director of the National Center of Excellence in Research on Solar Long-Term Variability and Effects, which is the RESOLVE program, I'm guessing, of the Academy of Finland. And his main fields of expertise, as you will see, cosmic rays, heliospheric physics, solar activity, and solar terrestrial relations. So I leave it to him to carry on. Thank you.
So, good afternoon, ladies and gentlemen. It's my pleasure to be here, and thanks for inviting and giving a chance to talk to you about some knowns and unknowns of long-term solar activity reconstructions. So I will briefly, or in some places not very briefly, tell about what can we learn about solar activity variability on long-term scale. Long-term scale here means beyond one solar cycle and up to several millennia. First of all, we all use terms solar activity, but what is it? Actually, there is no, it's not a physical term. It's some generic term used as the composed aggregate of different forms of solar surface and coronal transient phenomena, which are driven by the solar dynamo in the convection zone, and many different indices are used to quantify the solar activity. Probably the most famous is the sunspot numbers, and this nice plot in the center is actually drawing by Cassini, made in the year 1671 during the Maunder minimum. It just to illustrate that even in 17th century, the observers and instruments were good enough to resolve spots, umbra, penumbra, even making developments of the in time, because these are just different phases of the same spot location, although that's quite rare example from that time when the same spot was studied so carefully. Then, of course, many other indices used in the modern time, like emission of the sun in different wavelengths, heliospheric transients phenomena like coronal mass ejections and many other. But I will be mostly speaking of the sunspot activity, or actually the generic index quantifying the number of sunspots on the solar surface. Here I plot very schematically the history of solar activity studies. And of course, direct measurements like we do now in different wavelengths, spaceborne, cover only last decades. Then we have about 100 years of optical measurements, ground-based, which can be, of course, translated into different forms of solar activity. Approximately at the same time, about 100 measurements, 100 years, there are geomagnetic activity measurements, mostly like KP indices and others, which also driven by solar activity. Then there is the famous sunspot count or sunspot number series covering the last 400 years, but the quality, of course, becomes poor to earlier part of the series. So that's why color is changing here. That the further we go, the poorer is the quality of data. There are some aurora records of aurora sightings, but the quality again is quite poor in the earlier part, although it covers a millennium or so. And actually, the same relates to naked eye sunspot observations, which were fragmentary, recorded mostly by Oriental Chronicles. The problem is with these two records that they cannot be translated quantitatively into the index of solar activity. They only can indicate the overall level. And what I will be talking here mostly is about cosmogenic isotopes, which cover with roughly equal quality the last 10,000 years, and there is a potential of going even further. I will tell what makes it difficult to go beyond the 10,000 years. So if we plot the conventional sunspot series, what we can see, of course, the main variability is the 11-year cycle. On top of that, there is centennial variability, which shows the variability of the amplitude of the cycle. Then, of course, very clear is the Maunder minimum, where the solar activity was extremely low, although there was still an activity. And the contemporary level was quite high, but from that record, it's difficult to say, was it exceptionally high or just some deviations from the normal level. But now we are certain that this period of high activity ended, and the current cycle 24 is just a regular cycle. But we want to go beyond this 400 years. And here, the only way to do it is via cosmic ray variability at the Earth. And the main idea is shown here. So on the Sun, there is solar activity, which expands to the heliosphere via interplanetary magnetic field and solar wind. And it fills the heliosphere, and from outside the heliosphere, there is an influx of cosmic rays, which at that time scale can be assumed to be constant. Inside the heliosphere, cosmic rays are modulated by the interplanetary magnetic field. So then the modulated flux of cosmic rays reaches the Earth. And then there is another shielding, it's geomagnetic field, which additionally modulates the flux of cosmic rays, and finally they can hit the Earth atmosphere. So to say it very briefly, for the last several decades, when we have more or less direct data, it shows the sunspot variability. Quite important parameter is the tilt of the heliospheric neutral sheet, the open magnetic flux, which quantifies the global heliospheric magnetic field in the whole heliosphere, and solar wind in the ecliptic plane doesn't show big variability, but all this affects the cosmic ray flux, so that if we plot this energy spectrum of galactic cosmic rays outside the heliosphere, the black line, and at Earth, at solar minimum and solar maximum conditions, you can see that at the lower energy range, the variability of the solar modulation of cosmic rays is a factor of roughly 50. It's one order of magnitude at about 1 GeV energy, and goes and vanishes for higher energies. And additionally, there is geomagnetic shielding of the Earth, which leads to higher cosmic ray flux in polar regions and lower flux at tropical regions, and it also can change in time. So first idea is just to look at the direct cosmic ray records, as shown here. It's all cosmic ray count rate extended by climax, which is not far from here. Data for the last 60 years compared to sunspot numbers. The first idea is, okay, we can just use a simple regression or linear regression, because we know when there is minimum of solar activity, there is maximum of cosmic rays, and vice versa. An interesting thing is that sunspot number always return to 0 level at minimum, but cosmic rays have different variability, and the last minimum, this is year 2009, there was an exceptionally high level of cosmic rays, the highest ever recorded during the space era, or during the last decades. So probably linear regression would not work, and I will explain later why and how we deal. What happens when cosmic rays, which are very energetic, mostly protons or alpha particles, enter the Earth's atmosphere? First, they go through, but sooner or later, they will collide with one of nuclei of atmospheric gases, because the atmosphere is very thick for them. Because of their very high energy, the touched nucleus can be destroyed in parts, and these parts may have still sufficient energy to go further and suffer further collisions. This leads to so-called nucleonic shower or cascade. There are many other parts of this cascade, but we are interested mostly in the nucleonic part. In each of these collisions, with quite low probability, but some reactions like spallation reaction of oxygen, nitrogen, or argon can lead to very small amount of isotopes like beryllium-7, beryllium-10, and further on produced here. Or slow neutrons can be captured by nitrogen producing radiocarbon, carbon-14. Important point here is that all these nuclides can be produced in Earth only in this way. That's why they're called cosmogenic. With only exception for the last 50 years, that during nuclear explosions, people unfortunately can produce the same isotopes. But at least before that, it was the only source. So if we know how many of these isotopes were produced in the atmosphere, we may estimate the flux of cosmic rays in the past. That's the very idea of the method of cosmogenic isotopes. Then all this process can be modeled, and we may compute the theoretical production curve, which shows the amount of this for radiocarbon atoms per square centimeter per second as a function of the cosmic ray modulation potential, which parameterizes the spectrum of cosmic rays, and the geomagnetic dipole moment. So if we know the geomagnetic dipole moment independently, and we know the how many atoms were produced in the atmosphere of radiocarbon, we can evaluate the level of modulation of cosmic rays and accordingly the solar variability. A very important point here is the changes of the geomagnetic field intensity. It should not be mixed with geomagnetic activity. It has nothing to do with geomagnetic activity. It's just the large-scale geomagnetic field, mostly its dipole component. And here are shown different reconstructions of the geomagnetic field intensity, of the dipole moment, the virtual aligned dipole model over the last 9,000 years. And the variability is quite big. It's actually roughly a factor of 2, from 6 to 11 in these units. And different reconstructions vary quite a lot. On the overall profile, they agree, but the shorter scale variability is very different. And that makes the greatest uncertainty of the method, because the geomagnetic field must be known independently in order to apply the method. I will be speaking mostly of two cosmogenic isotopes, most useful, and these are radiocarbon, carbon-14, and beryllium-10. They are different in many senses, and that's good for us because we can compare. First, I will speak about the overall idea. So the flux, incoming flux of cosmic rays is modulated in the heliosphere, additionally by geomagnetic shielding. Then there is production in the atmosphere, where radiocarbon takes a form of gas, CO2 mostly. So it's in gaseous form. And for beryllium-10, it gets attached to aerosols. So it follows the path of aerosols and quite quickly precipitate, while the radiocarbon takes part in the entire carbon cycle. Then, of course, climate can affect all these links between atmosphere and ocean, biosphere, between stratosphere and troposphere. And that makes it difficult to go beyond the 10,000 years, which is the duration of the Holocene, the last quite stable warm period, where we may assume very roughly that the climate is more or less stable. So we can apply the modern day conditions, which are quite known, and extend them back. When we go to deglaciation or glacial period, we just don't have enough data to estimate the carbon cycle, for instance, although some models try to go there. And if there is this connection between solar activity and climate, it makes the reconstruction quite tricky. But as we know, probably it's not very strong of providing a feedback for the model. So how it all looks for radiocarbon first. These are what is measured. It's the relative concentration of radiocarbon. It's mostly done in 3 rings, so that there is absolute dating via dendrochronology, corrected for the decay. So the curve looks like that. And after applying a carbon cycle model, we can reconstruct the production rate. Because once it's produced, it stands in the whole system. It's very complicated, so you can hardly estimate anything from direct measurements. You need to deconvolute it to the production. But since we know quite well the carbon cycle model, and again, thanks to bomb tests, it's probably the only thing we can thank the bomb tests, the model, radiocarbon model, is very well calibrated, because a huge amount of radiocarbon was produced during atmospheric bomb tests. We know exactly the place, time, and more or less the intensity, so the model can be well calibrated. Okay, that's a classical view of a carbon cycle in the form of box model, multi-box model. It looks quite complicated. Sometimes some boxes are combined, but roughly there is always an exchange with the typical time between different reservoirs. Production is here, and then it spreads over different reservoirs. Oceans are huge reservoirs, so they are very important, because they just dump there almost radiocarbon, and then they keep it releasing into the atmosphere, which makes it so difficult to reconstruct. But again, the model is quite well developed. And this is a modern way developed in the University of Bern recently, where a climate model with dynamic scale is combined with this with the boxes, so it's not anymore box. It's dynamic and self-consistent model of a carbon cycle, which makes it possible to estimate quite reliably the production rate of the radiocarbon. For cosmogenic beryllium-10, it's much easier. There is no cycle. It's just produced in the stratosphere and partly in the troposphere, gets attached to aerosols and precipitates quite fast into the ice. The problem is that deposition here plays an important role. If you change deposition, the measured signal can be distorted. And this just shows some model of beryllium-10 wet precipitation in different regions. And you can see that, well, ice sheets where the beryllium is measured, it's measured in ice cores with relative dating. These are from Antarctic and Greenland. Antarctic is a nice place because the precipitation here is quite stable. In Greenland, it's more difficult. You can see there is a gradient between northern Greenland and this region of a factor of 3 to 5. A small change in precipitation can disturb the solar signal there. But the idea is that the two isotopes, radiocarbon and beryllium-10, are very different in what happens to them in the terrestrial system. And therefore, if there is a common signal, we may say that it's production, because the redistribution is completely different pattern. So then first what we try to do is to make a model of cosmic ray variability based on sunspot numbers with the semi-empirical model of the open solar magnetic flux and other, and compare it with the data. These are real observations of cosmic rays, and then the model predicts that the cosmic ray variability over the last 400 years should be like that, with the Dalton minimum and Maunder minimum. Fortunately, the model doesn't work inside the Maunder minimum, so it's. But if we compare it with data, with direct measurements of beryllium-10 in Greenland, blue line, and Antarctic, blue dots, with the model, it's not really reconstruction, it's just direct computations by model. The agreement is quite well, suggesting that we are on the right track, at least, with the modeling. And we even, for the last 100 years of data, when the data are quite good, we are even able to predict exactly the magnitude of 11-year cycle in the beryllium-10, except of this maybe cycle. Points here are measurements, and the two curves are two different models. So what we do here, again, we start from sunspot numbers. We compute the open magnetic flux from sunspot number. We compute the cosmic ray flux. We compute beryllium-10. And that's what we get. It's pure computation. No normalization, just straightforward. And then compare with the data. Agreement is almost perfect. So we really can model the process. The same goes for radiocarbon. Again, from sunspot numbers, we compute via the open solar magnetic flux. We compute the production of radiocarbon. The computed curve is red. The measurements are green. Again, the agreement is quite nice. You can see the Dalton minimum and the Maunder minimum. Okay, so the model seems to work. Now we can try to invert the model. We know the measurements of cosmogenic isotope. Let's estimate the sunspot number inverting the model. That's what we get. The blue curve is sunspot number. This is the modulation potential, which is an index of cosmic ray modulation. We'll go to sunspot number later. Based on radiocarbon, the blue curve, and the composite of several series of beryllium-10. The agreement is, again, nearly perfect. There are some discrepancy at short time scale, but overall, they agree quite well. Again, if we compare now the sunspot number reconstructions with measurements. The agreement is here. The blue line is reconstruction from radiocarbon, and red line is group sunspot numbers. The agreement is quite well, except of this point. So we may say that it seems to work. Then we go to longer time scale. This is a reconstruction by Stein-Hilber, and this reconstruction by our group from radiocarbon. This is just extension of the scale. So there is quite a lot of variability, but interestingly, there are some periods when the activity is very low. And these are Grant minima, like the Maunder minimum. So we know that Maunder minimum is was not the only minimum. There are many. Well, of course, in some cases, like here, we cannot say whether it's really minimum or not, but anyway, we know there are many. For the Grant maximum, was what was the last 50 years, probably. There are also some periods of similarly high activity, but again, it's not easy to define them. But at least if we put some threshold, that in this reconstruction we got 27 Grant minima over the Holocene, or over the 11,000 years, 19 Grant maxima, and the time spent in these states is roughly 1/6 for Grant minima and about 10% for Grant maxima. Simple analysis shows that there is no clear periodicity in the periods of this event, but there is some quite apparent clustering of Grant minima with a period of about 2,500 years. That's called the Hallstatt cycle. You can see here is a cluster, here is a cluster, here cluster, here cluster. And inside this cluster, there is quite clear periodicity of about 200 years between the Grant minima. This is also known as Zeus or de Vries cycle, which is known in solar activity. And no apparent periodicities for Grant minima is found. They seem to appear quite randomly. Now, if we consider reconstruction of solar activity only for the last 3,000 years, when the geomagnetic field is quite well known, quite well defined, the issue is that for reconstructions of the geomagnetic field intensity, the most useful method is archaeomagnetic data, which means in archaeological site, when you use some pots, at the moment when they were produced, they fix the magnetization there. So you may reconstruct the local magnetic field at that place at the time when this pot was produced. And independent archaeological dating gives you the date for this event. And there are many, many sites for the last 3,000 years. So there is more or less global coverage. The reconstruction of the global geomagnetic field intensity is quite good. But when we go further back in time, there are less and less archaeological sites. There are less and less archaeological data. So then what remains? Only the sediments, lake sediments, for instance, or wharfs, which are quite sparse and they give lower quality of data, or volcanic data. Lava, when it gets frozen, it makes the same exactly as spots. So these measurements are good, but there are not so many volcanoes. So for the last 3,000 years, the data are good. So we expect that the reconstruction is robust. And the recent reconstruction of solar activity based on radiocarbon is shown here. And what's interesting here, you can see that it almost stays at the same level, except a few clear event of Grant minima. And the red curve shows the classical group sunspot number. Now, what we do probability density function of the sunspot numbers. Just this. Since we have an ensemble of reconstructions based on Monte Carlo for taking account uncertainty, we have quite good statistics. And what we see, there is a clear bimodal distribution. So we have the main mode, regular mode, and quite separate mode for grand minimum conditions. And interestingly, if we fit it with Gaussian, the distribution is more sharp here than just from the Gaussian. So it's more concentrated. Then actually, if you want, you can see some small bump here. But statistically, it's not significant. So you cannot say there is another mode here. We want to see something there, but statistically, it's insignificant. Just for a better presentation, one can make a kind of trick. So from a distribution like shown on the previous plot of PDF, removing the best fitting Gaussian. That's what remains here. You can clearly see here one, the regular mode as a red point. So the distribution, the concentration of the values here is higher than expected from Gaussian. A second mode, the grand minimum mode here, again, it's quite clear for the last 4,000 years, but then get dispersed, probably of the low quality geomagnetic data, and some very, very weak hints for the grand maximum mode. That's the best we can do now. We need better geomagnetic reconstructions for it. Yes? Okay, so okay, here in this plot it's only one, but we can use this plot. Yes, it's based on this data because for that period, actually, we have quite useful for statistics an ensemble of. It's INTCAL data set, which includes global global locations. So many different trees from different locations have been measured and put together. So it represents the global radiocarbon. They say that it's globally averaged. For beryllium-10, you can only use one location because the production is more or less regional. Then you ask that you lose the connection between the cosmogenic isotope and sunspot number. Should I repeat it? Ah. Okay. Actually, this but volcanic eruptions and droughts have nothing to do with radiocarbon. Oh yes, sure. If there is no trees, there is. But this is INTCAL data again, which use for different periods from 5 to 20 trees from all over the world, from different regions. So it's a huge work done by the INTCAL collaboration to produce the calibration curve. Their main interest is not solar activity. For them, it's a disturbing signal. the main issue is dating. It's a kind of industry. They invest a lot of money into provide calibration curve for radiocarbon data. Because of that, the quality of the data is perfect. I mean, for at least it's better than for beryllium-10. There is much more effort on calibration, on relative calibration, and on composition of the globally average data. Of course, one can go to individual trees, but we didn't do it. We do trust the INCAL collaboration in providing the global average data. But again, I will show that radiocarbon and beryllium agree very well. So some observational facts about the what we see from such reconstruction. Though solar activity is quite variable. Recent solar activity was a grand maximum, but now it's fading. The sun spends about 3/4 of time in the moderate activity, 1/6 in grand minimum, and about 10% in the grand maximum state. The numbers are very rough, but it seems to be like that. And the occurrence of grand minima and maxima is not a result of long-term cyclic variation, so it's not periodic, but defined probably by stochastic chaotic process, and this poses quite a constraint for solar dynamo. And then I will quite briefly describe what other we can do with the cosmogenic isotopes. So from terrestrial archives, as I mentioned, radiocarbon in 3 rings and beryllium-10 in ice cores, we can reconstruct cosmic ray or solar variability in the past. Also, we may perform direct search for extreme solar energetic particle events. Also, cosmogenic isotopes in meteorites can be used for direct test of reconstructions. I will show in a few slides. And cosmogenic isotopes produced directly in lunar rocks can be used for to estimate the average solar energetic particle flux in the past. Also, indirect assessment of the solar energetic particle events, and they help estimating the average galactic cosmic ray flux, but I don't have time to go to all this. So I will only give a few brief results. We can test solar activity for the last centuries, like what I shown earlier, that the models reproduce quite well observations. Just a short example, quite recently, maybe a month ago, there was a new group Sunspot series released by Live Svalga, paper in archive, suggesting that the solar activity was much higher than we thought before in that period, in the 17, 18 centuries. We can do the same tour as we did before. We put this sunspot number into the model. We compute the radiocarbon. It's a blue curve. What we get, systematic offset, although they agree in the beginning of the series when the sunspot number are correct. So it seems that, at least from the point of view of cosmic rays, this new suggestion overestimates the cosmic ray modulation. I'm not speaking about sunspot activity. I'm speaking about cosmic ray modulation. It overestimates it. We can also use the meteorite data. An advantage of meteorites is that cosmogenic isotope, the most useful is titanium-44, is produced directly in the body while the meteorite is flying in space. But disadvantage is that there is no time resolution. It's always a balance between production and decay. But once it falls on the ground. There is no production in situ anymore. So if we measure titanium-44 in a fallen meteorites, of course correcting for the decay, we will know the mean balance or the mean cosmic ray flux before the fall of the meteorite for about 1 to lifetimes. And half-life is about 60 years. Gray dots are the data of the meteorites. Titanium-4 measured in about 20 meteorites fallen during different times. And the curves are the computed titanium-44 activity in E in this case, which is, again, we know more or less the orbit of the meteorite, so we can compute how much titanium-44 was produced and decayed during this flight. And the reconstruction, group sunspot numbers is red curve. Green is the data from radiocarbon. The pink curve or magenta curve is beryllium-24, and the blue curve again is computed using the this higher estimate of the solar activity. Again, it's not consistent with the data suggesting that it overestimates the cosmic ray modulation. Excuse me? What? Because the reason is here. It's much higher sunspot numbers should result in much higher modulation of cosmic rays if we trust the model. Then we directly compute the production of cosmogenic isotope. No, we cannot account for that. So we assume that the deposition is constant, just on a relatively short time scale of tens and 100 years. Beryllium is much more noisy because of the local climate and the deposition changes. So here it's a bit higher, here it's a bit low. That's difficult. But I don't remember. It doesn't mention here. No, I think it's from Greenland. So very quickly, a few more minutes. Are we going from space storm to space calm? So how unique is the current cycle 24? At least it's unique for the space era, for direct measurements. It's very low comparing to what we saw before. But if we compare to the longer time scale, this line shows the level of the minimum and maximum of the current cycle in cosmic rays. We can see that it's quite comparable in the turn of 19th and 20th centuries, and also in the middle 18th century. The same goes if we try the open solar magnetic flux reconstructions independently by Lockwood et al. And Max Planck group. The open solar magnetic flux is very low now comparing to the last decades. But still, it's higher than we expected during the Maunder minimum, although this zero is not correct. It should go somewhere here. It's just a problem of the model. Again, it's comparable to the mid-18th century and turn of 19th and 20th century. And if we go back to the 10,000 years, this is the level of the cycle 24. Since this is not an amplitude, the mean value, then it seems to be quite normal amplitude of the cycle, not something specifically low. So what actually was unusual was it was quite high level of activity for the last 50 years, but now it returns to the normal level. And as a summary, what we do know with some level of confidence is that the main cause of cosmic ray variability is related to solar magnetic activity, that cosmic ray variations as measured via cosmogenic isotopes is the only source of information of solar and heliospheric activity in the distant past, where we don't have direct data. Solar activity varied quite essentially from the regular stable mode with grand minima and grand maxima. These are quite distinct events. The modern grand maximum is over. At the current weak solar activity level is, in fact, normal one, not really weak. And unknowns. The very long term, here I mean multi-millennium, trend in solar activity may be uncertain because of two things. The main uncertainty is the geomagnetic field in the past, before the 3000 roughly BC. And also, all models assume more or less stability of climate during the Holocene. So if there was long-term climate variability, especially in ocean circulation for radiocarbon and large-scale atmospheric dynamics for beryllium-10, it may add uncertainties on the long-term scale. Some grand minima and grand maxima defined in reconstructions can be less certain because of the noisy data, so we may identify some wiggles as the events, but these uncertainties can be constrained using multi-proxy records from different isotopes, and that work is in progress. Thank you.